In this video, we are going to apply PCA in a dataset to reduce the dimensionality or the dimension of the dataset. PCA, or the principal component analysis, is a dimensionality reduction technique which is frequently used in machine learning methods or in machine learning models. The problem states, for a given data set as in table 1 with two features x and y and 10 data points 1 to 10, we are supposed to apply PCA so that the features or the dimension, which is 2 in the given data set x and y, we need to reduce into a dimension of 1. That means we need to eliminate one of the feature, either x or y, and the final resultant data set will have only one feature, either x or y, which is known as principal component, and then the classification. Here x and y are two independent variables and class is a dependent variable. Please note, the PCA is applied on the dataset to reduce the number of independent parameters, independent features or variables. Since we have two independent variables or features x and y, that is why the dimension of the current data set given in table 1 is 2, dimension is 2, and the total number of data points are 10, which is called n is equals to 10, which is called the sample size. Sample size is 10. Based on the given facts with two independent features and n equals to 10, which is the size of the size of the sample, we are supposed to apply the principal component analysis technique so that we can reduce the dimensionality of the given data set from 2 to 1. The process of dimensionality reduction using PCA is centered around the covariance matrix formed by finding the covariance between every pair of independent features. In order to apply the PCA, we have to find the covariance of each of the features x and y. The covariance is a statistical tool used for revealing the relationship between any of the two features in the dataset. Covariance gives either a positive number if variables are positively related, and it gives a negative number if they are negatively related. A higher value of covariance indicates that there is a strong relationship between the variables, and a low value indicates that the relationship between the two variables are weak. So since we have two variables x and y, so we need to find out the covariance between x and x itself, x and y, y and x, and y and y. So there are 4 covariance we have to compute. Based on this computed covariance, we need to find out the covariance matrix, as this side we will have x, this side we will have y, then this side we will have x and y. Then the covariance matrix will be formed as the computing the value of covariance of x, x, covariance of x, y, covariance of y, x, and covariance of covariance of y comma y. Moreover, covariance of x comma y is equals to covariance of y comma x. The covariance of any two variables x and y is computed as the sum of all xi minus x bar multiplied by yi minus y bar. I varies from 1 to n, where n is equals to sample size 10 in our case, and x bar is the mean of all x values. Y bar is the mean of all y values. Then we will multiply the values of x minus x bar for all x's with y minus y bar for all y's. Then the sum will be divided by the sample size n minus 1. Similarly, if we wanted to compute the covariance of x comma x, then it will be, the formula will be given by, this part will remain same. Here I is equals to 1 to n x minus x bar whole square, and covariance of y minus y and y is equals to, similarly I equals to 1 to n y minus y bar whole square divided by n minus 1. Also, covariance of x comma y is equals to covariance of y comma x. Now we will see how can we compute these values of covariance between two variables x and y. To compute the covariance matrix, we have evaluated few data from the given data set. For example, we have computed the mean of x, mean of y. We have also computed the x minus x bar whole square, x minus x bar into y minus y bar, then y minus y bar whole square, which we will use in computing the covariance matrix. Now let us see how to put these values in the covariance in order to compute the covariance matrix. To compute the covariance matrix, first the covariance of x comma x, which is computed using this formula, the value of x minus x bar into y minus y bar summation for all the points, which we can have it from this component 1.781 divided by n is equals to 10 here, divided by 9. This value, covariance of x comma y, which is computed as dividing the value of x minus x bar multiplied by y minus y bar summation, which is 0.176 divided by 9. Yx, covariance of yx is equals to covariance of xy. That's why this value will be 0.176 divided by 9. And covariance of y comma y, which is evaluated as the sum of this component y minus y bar whole square, which is equals to 2.176 divided by 9, and these values gives us the values as 0.198. This value is computed as 0.021. This value is computed as 0.021, and this value is computed as 0.242. Finally, the covariance matrix is given by 0.198, 0.021, 0.021, 0.242. Let us assume that this covariance matrix is denoted by A. This is the first step for PCA computation, and after computing the covariance matrix, next step is to find the eigenvalue, and eigenvector. In the next step, we will see how to compute the eigenvalue and corresponding eigenvector for the computed eigenvalues. So far, in the computation of PCA, we have found out that A, the covariance matrix, is given by 0.198, 0.021, 0.021, 0.242. After generating the covariance matrix, now we need to find out the eigenvalue and eigenvector, eigenvalue and respective eigenvectors. To compute eigenvalue and eigenvectors, let us assume that lambda is the eigenvalue and I is an identity matrix of 2 by 2 denoted as 1 0 0 1. This is the identity matrix of 2 by 2. To compute the eigenvalue, or to compute the value of lambda, to compute the value of lambda, we have to solve the equation determinant of A minus lambda I equals to 0. So if I compute lambda I, it gives you a matrix of the type lambda 0 0 lambda, and A minus lambda I gives us 0.198 minus lambda, 0.021, 0.021 and 0.242 minus lambda. We get this matrix A minus lambda I. And now if we take the determinant of this matrix, A minus lambda I gives us the value. We will multiply these two components and minus multiplication of these two components, 0.198 minus lambda into 0.242 minus lambda minus 0.021 multiplied by 0.021. If we multiply all the components, then we get 0.048 minus 0.198 lambda minus 0.242 lambda plus lambda square minus 0.0004, which is computed as lambda square minus 0.44 lambda plus 0.048, and which is equals to 0, which is assigned to 0 in order to find the value of lambda. If we solve this quadratic equation, then we can have the value of lambda, which is the eigenvalue for the given covariance matrix. The equation derived in the previous step is lambda square minus 0.44 lambda plus 0.048 equals to 0. If we compare this equation with the generalized quadratic equation ax square plus bx plus c is equals to 0, and performing the operation of x is equals to minus b plus or minus square root of b square minus 4ac divided by 2a, then we can compute the values of lambda. In this case, a will be equals to, in our case, a will be equals to 1, b is equals to 0.44 minus 0.44, and c is equals to 0.048. Putting these values of a, b and c, lambda could be computed in the same way: minus b plus and minus square root of b square minus 4ac divided by 2a. Substituting the values of a, b and c, lambda is given as minus 0.44 plus minus square root of b square, b is again 0.44 minus 0.44 whole square minus 4 into 1 into value of c is 0.048, 2 into 1, which is equals to, so this is equals to 0.44 plus minus 0.02. So lambda is equals to 0.44 plus minus 0.02. Hence, the first eigenvalue will be lambda 1 is equals to 0.44 plus 0.02, and second eigenvalue will be lambda 2 is equals to 0.44 minus 0.02. This is equals to 0.46, and this is equals to 0.42. According to the PCA, since we are interested in only one variable x or y, we have to arrange these values in descending order, where we get lambda 1 is greater than lambda 2, and so we have to consider the eigenvalue lambda 1 in order to compute the eigenvector. As we have discussed earlier, we have to consider the component with highest eigenvalue. Here lambda 1 has the highest value, so we will consider lambda 1 for computing the eigenvector, and that will in turn give us the principal component that should be used for future computation.